Welcome to this evening's flipped lesson on Introduction to the Atom. Okay, well, as we get further into this unit, Nature of Matter, we've covered what matter is. We've listed and described the four states of matter: solid, liquid, gas, and plasma. We've listed and described and provided the terminology for changes between states of matter, such as melting and freezing. We've learned sublimation and deposition. We still need to spend some more time on physical versus chemical properties and changes, as well as classification of matter, but we're far enough into the introduction to this unit to begin to talk about the main topic of this unit, which is the atom and the modern structure of the atom and atomic properties and behavior. This is a fascinating story, one of my favorite topics in the course, and I think you're going to enjoy this. All matter is comprised of atoms. And remember, previously we had said that matter is anything that has mass and occupies space. Well, if you put two and two together, now we can say that, well, the mass of matter has to do with really the type and number of atoms that comprise that matter. And the space, part of the definition, has to do with the space that those atoms occupy. Now, the word atom comes from the Greek atomus, and that means uncuttable or indivisible. And it's not a bad thing to call an atom. It works for most purposes. It will work for most of our purposes. We won't be cutting or splitting atoms in this course. That's an area of chemistry called nuclear chemistry. And so, yes, as the simplest component of matter that retains the properties of an element, then the Greek root is a perfectly fine term. But as something that literally cannot be cut, then the Greek root doesn't work as well, because atoms can be cut, can't they? They can be split. We do it every day. How is that possible? Yes, we cut atoms every day. We split them every day in the process called nuclear fission. This is something that humankind has known of and known how to do since World War II. In fact, it ended World War II. And we can use this process for terrible weapons of mass destruction, like the atomic bomb that was dropped on two Japanese cities to end World War II in 1945. Or preferably, we can use this for peacetime electric power generation. You see that in the upper right. That's a nuclear reactor. And both of these applications depend on the same chemistry, the same nuclear chemistry, and that would be the splitting or cutting of a uranium-235 atom. You can see that in this chemical equation. A U-235 atom collides with a neutron and is split into what are called daughter products, into a barium-145 atom and a krypton-92 atom and 3 neutrons and a lot of heat energy and a lot of light energy and a lot of radiation energy. And so certainly this is a common process now for humankind, and atoms are certainly cut or split in this process. I want to focus on those 3 neutrons, which you see on the right-hand side of that chemical equation. The right-hand side of an equation are the products of the reaction. The left-hand side are the reactants. And so those 3 neutrons remind us that the atoms themselves are comprised of even smaller particles. In fact, there are 3 of these particles, the 3 subatomic particles. And so here are the 3 subatomic particles. In fact, in the order of their discovery, the electron being discovered first and the neutron being discovered most recently. I think it's both interesting and important to understand some of the history behind some of the more important discoveries in science. And so the electron was discovered by the great English physicist J.J. Thomson. In fact, we're gonna be looking at his cathode ray tube experiment in more detail at a later time. And Thomson was a professor at Cambridge University, working in the very, very famous Cavendish labs. You'll see that name pop up a lot in this unit. Robert Millikan of the University of Chicago, an American, performed an experiment about 10 years later, a little bit more, which gave us more information about the electron. And so the proton, the second subatomic particle, was discovered and characterized a few years later in the same famous labs at Cambridge University by Ernest Rutherford in his famous gold foil experiment, which we will also spend more time with at a later time. And what's interesting is that Ernest Rutherford had studied under J.J. Thomson, and the gold foil experiment shed light on the nature of the proton, which was completely inconsistent with the model, the original model that J.J. Thomson, Rutherford's advisor, had first proposed. So here's an example of the student doing better than the teacher. Finally, our third subatomic particle, the neutron, was discovered by James Chadwick in 1932, quite a few years later. Again, though, in the same location, the Cavendish Labs at Cambridge University. So certainly Cambridge is a center of excellence for the physical sciences. Well, this is a very important table because it provides a lot of information. It summarizes the properties and characteristics of these three subatomic particles. And we're going to be spending a lot of time. You're going to be hearing a lot about electrons, protons, and neutrons from this point forward until the end of the year. I mean, this is the basis for theoretical chemistry. And so let's start with the electron. So as you can see in the table, the electron has an electric charge of -1. It's a negative charge. It's like the negative pole of a battery. It has a very tiny mass, expressed in grams. That's 10 to the minus 28 grams. So that's a decimal with 27 zeros followed by a 9. And here our knowledge of units comes in handy. We can also express the mass of these three subatomic particles in units called atomic mass units, or AMUs. And those are relative mass units, and we'll say more about that at a later time. The electrons are located, their location within an atom is outside the nucleus of the atom. And the nucleus, you may know, is that small central region of an atom, very, very dense, very, very small. So the electrons are located outside that region, outside that nucleus. The proton, again, continuing reading across from left to right, has an electric charge of +1, or a positive charge, and has a mass that may be very small in grams, but is much greater than the mass of the electron. You can see that especially when we list the mass in atomic mass units. The proton is located within the nucleus, making it one of two nucleons, the other being the neutron. Nucleon being a particle that's located within the nucleus. And finally, the neutron has a charge of 0, hence the name neutron for neutral, electrically neutral. It has a mass just slightly greater than the proton, essentially the same mass. Both of them are much greater than the electron, and it also resides in the nucleus, making it a nucleon. Now, there's one more thing I want to say here, which is that if you were taking this course 15 years ago or 20 years ago, let's say 15 years ago, then these would be the fundamental smallest particles of matter, if you will. But about 15 years ago, a tremendous discovery was made that in fact the subatomic particles themselves are comprised of even smaller particles that are called quarks. You can see that typed in at the bottom of the screen. We're not going to spend much, if any, time on quarks. That's outside the scope of our course. That's in the realm of nuclear physics, really. But that's a very, very important active area of research in nuclear physics today. Well, tables of particles and their properties are all well and good, but we want to understand how these particles work within atoms. So let's begin to look at that. Here's a representation of a lithium atom, and really what you're looking at here is a classical what's called Bohr, B-O-H-R, after the famous Danish physicist Niels Bohr. So it's a Bohr representation of an atom, and that basically means that in the middle of the diagram, you list the protons and the neutrons, and you can see that here. The protons are red spheres with a plus sign, and the neutrons are gold spheres with a 0 sign. And then outside protons and neutrons, you have the electrons, and they seem to be orbiting the nucleus containing the protons and neutrons. I say seem to, because the analogy between planets orbiting the sun, which is what this looks like, and electrons that reside outside the nucleus is a very poor analogy. So I want you to know that. But for our purposes, this model, at least at these early stages, is helpful. So here's a representation of a lithium atom. Now let's look at the element lithium in the periodic table. And lithium occurs in the first column. We call the columns groups. We call the columns groups and the rows periods. So the columns of the periodic table are groups, and so that's the first group, group 1, and it's the second element in the first group, and it's also enlarged so we can see some of the detail to the right. So in other words, you see where lithium actually occurs in the periodic table. That red arrow is pointing at it. And then to the right of lithium is beryllium, Be. And then to the right of beryllium, again, is lithium. It's just enlarged so we can see what's going on. Notice that the 3 protons in the nucleus of a lithium atom correspond to the 3, which is the number above the symbol for the element. All right, and in fact, that's a very important property of an element, or an atom of an element, and that's called the atomic number. And so we can learn that right now. Okay, well, in this screen, in the lower left, you see the information on the element lithium that we get from the periodic table, repeated. You see our sketch in the upper left of a lithium atom, repeated, and you see some typed information. Let's go through the typed information. There are 3 protons in the nucleus of a lithium atom for a total charge of 3+, a total electric charge of 3 positive charges, and a total mass of 3 atomic mass units. There are 4 neutrons in the nucleus of a lithium atom for a total charge of 0, since these are neutrons, but a total mass of 4 atomic mass units. And finally, there were 3 electrons outside the nucleus for a total electric charge of 3 minus, 3 negative charges, and a total mass of 0. And again, we know that electrons do have some mass. We saw that in the summary table, but their mass is so small that we say they're massless. Now, I'm going to say something here, and you're going to hear me say this many times because it's so important. The proton count, those 3 protons in the nucleus of a lithium atom, which is something called the atomic number. I think we mentioned that in the previous screen. It's the atomic number, the proton count, that make that atom an atom of lithium and not an atom of some other element. want to say that again. It's the proton count, the 3 protons in the nucleus of that atom, the atomic number of 3, that make that an atom of lithium and not an atom of uranium or sodium or sulfur or selenium. And the implication of that statement is that you can have lithium atoms that have a neutron count other than 4. You can have lithium atoms that have an electron count other than 3. But you can't have lithium atoms that have a proton count other than 3, because then they're not lithium atoms anymore. So this is something that is worth saying a lot. Okay, this is the last screen for this evening, and I want to point something out. Notice that the 3 protons and the 4 neutrons add up to a mass number of 7. 3 atomic mass units for 3 protons, 4 atomic mass units for 4 neutrons, 3 and 4 add to 7. But notice that there's a number below the name of the element in the periodic table, which is almost 7, 6.941. That number is an atomic mass. It's the atomic mass of the element lithium. And so I want to leave you with this question, interesting question. How is it that lithium atoms have a mass number of 7, but an atomic mass listed in the periodic table of not only a number that isn't 7, but a number that's fractional? How can you have a fractional atomic mass? You can't have fractions of protons and neutrons. So how is that possible? I'm going to leave you with that question. Okay, I hope you've enjoyed this flipped lesson on the introduction to the atom. Don't forget, please, to fill out the questionnaire that is also posted in Google Classroom along with this PowerPoint audio video. And have a good evening.